Come on, notepad. And sorry, this should say how many, roughly, how many moles are in. Okay. Right, so the first question, what you need to do first is get the mass on the left. So you can see that's 2.01410 plus 2.01410. So on the left, yeah, let me write it down here. Come on, pen. Number 1. The mass on the left is 4.0282. And the mass on the right, oh sorry, that's AMU of course, atomic mass units. And the mass on the right would be, let me see, the helium-3, 3.01603, plus a neutron, 1.00867. Right, so the mass on the right is 4.016897. So the mass that's missing is 0.011303 AMUs. Right, now, atomic mass unit, I was just using 1.66 earlier, wasn't I? So I'll just stick to using, wasn't it 1.66? I'll just stick to using 1.66. Times 1.66 times 10 to the minus 27.
How do you get 4.061689?
It's this one, helium-3 plus a neutron. That's helium-3. You distracted me. What was I saying now? Times 3 times 10 to the power of 8 squared. Okay. So the energy is mc squared, which will come out to be 1.69 picojoules. Or if you want, in a mega electron volts, that's 10.54 mega electron volts. Okay, next one. Yes? What's wrong, KJ? What's wrong? What?
The neutron and the helium.
4.0247. 3.01. Oh, I typed it in wrong. Plus a neutron. Oh well, lol for me. Okay, can you give me the correct answer then? That's not right. What was it? 4.0247, yes? Yes. Alright, so what's the correct answer then? The energy.
5.229 times 10 to the minus 23.
5.2?
Yes.
9. So 5.23 picojoules, yeah?
It's minus 23.
Minus 23? Are you sure? You're not messing with me? I don't trust you now. Right, let me double check. Right. We think this one's wrong. Okay, let's fix it. Right. 4.0247 minus 4.0282. Okay, times 10 to the power of minus 27. What's AMU? 1.66 times 10 to the minus 27, isn't it? 5.81. Okay. No, sorry, KJ. I got 0.523. What did you get, Tekken? Okay, yep. 3.26 mega electron volts, is it? No, I forget about the electron volt, I didn't ask for it. 0.523, wasn't it? Anyways, let's move on. We're just having trouble with our calculator. Come on, let's move on, please. Yes? Mm-hmm. Okay, next. Right. Let's check it together. So I'm getting the mass on the left to be 235.044 plus 1.00867. What's the mass on the left in number 2? 236.05267 AMU. Now the mass on the right, kryptonite plus 3 neutrons, and I get on the right, plus barium, which is 235.86941 AMUs. So the missing mass um 0.18326 AMU. Or if you want in kilograms, that's 3.04 times 10 to the minus 28 kilograms. So the energy would be mc squared 2.74 times 10 to the minus 11 joules. Okay, no? Yes? Mm-hmm. Right. So then, is that the A part? Yeah. The B part, roughly how many moles are in 1 gram? Well, the number of moles will be roughly 1 over 235. So that's roughly, not much, 0.00426 moles about.
For the mass on the right,
yep.
What did you add to get 235?
I added barium plus krypton, or kryptonite, plus 3 neutrons.
3.
Yeah. Ooh, dang. This is where I went wrong?
Yeah.
Okay. C. How many uranium-235 nuclei are there? Alright, so this is just good old Avogadro. N equals Na multiplied by N. So that's 0.00426 multiplied by my friend Avogadro. What is Avogadro's number? 6.02 times 10 to the minus 23.
Good.
So, no, plus 23, not minus. That'd be a big problem. So I get here 2.56 times 10 to the 21 atoms or nuclei. Okay, so no surprise, there's lots of uranium-235 atoms in a gram of uranium. How many reactions can you make with 1 gram? Well, look here, look. For each reaction, how many uranium atoms do you need? 1, yes? So how many reactions can you make? Well, the answer is 2.56 times 10 to the 21 reactions, because that's how many atoms you have. So how much energy can you make in total? Well, it will be 2.56 times 10 to the 21 times 2.74 times 10 to the minus 11. .01 times 10 to the 10 joules.
That's cheap.
Yes, it is. For 1 gram of uranium, you can make 70,144 megajoules of energy. So the next part now is, if a small city requires 10 megawatts, how long could 1 gram of uranium last? Well, what's the formula for power? Work over time. So time is work over power. So that's 7.01 times 10 to the 10. And I need 10 megawatts. So that's 10 times 10 to the 6. Wait, is it? Yeah. So that is in seconds. So in hours. So in days.
Days. So
Yeah, actually, let me double check that now. 7.01 times 10 to the power of 10 over 10 to the power of 7. Right, so that's seconds. Okay, that's better. Alright, so this is, time is roughly, it's 1.95 days, so it's nearly 2 days. It's, it's about 2 days, nearly. So think about that, 1 gram of uranium, you can release, if you can separate it, you can release enough energy to power the city for 2 days in 1 gram. Now, what we'll need to have, I know we have more questions to do, but what we need to have a look at next time, not today, is how do you do this reaction to release the energy? Okay. But anyways, what is the mass defect of copper 63? So copper 63 well, it should have 34 neutrons and how many protons? 29 protons, which is what's 1 point. So if you do here 29 protons plus, what did I say? 34 neutrons, this is equal to 63.5059 AMU. But the actual mass of copper is 62.91367 AMU. So, yeah, so the difference, the mass defect,
I don't know, someone got 62.5.
29 times the mass of a proton plus 34 times the mass of a neutron. That's what the mass of copper 63 should be. Continue.
What is mass of the two?
It's right here. There, 1.00728. AMU, which in kilograms is 9.83 times 10 to the minus 28 kilograms. So therefore the binding energy, which is mc squared, so the binding energy is in picos 88.48 picojoules. That's the binding energy. And the last part is what is the energy per nucleon. So there's 63 of them. So if I just take the energy and divide by 63, I'll get 1.4 picojoules. Or if you want, by the way, that's wait. That's roughly 8.77 mega electron volts. Now, if I just go back to my graph here, let me just see. Yeah. So copper is 63. So 63, 50, 60, 70, 80. Yeah. So 63 would be about here. So if I go up, now each of these they're quarters. So it'd be about 8.25, somewhere around about this. So it's not too bad, okay? You kind of get the right size of a number here. Right, so we don't have anything to do with that then next time. So just before I go, I just want to check what the next lesson is we'll have to do. Video. No, not video, sorry. Dropbox. DIFC. Physics. Atoms. Yeah, so next time, nuclear fission and fusion. Then photons, then quantum mechanics. Okay. Single hour tomorrow, yeah? Mm-hmm. Yeah, so we'll do the lesson 7 tomorrow then.